When German reconnaissance aircraft returned from missions over Britain in late January 1942, their cameras captured something new, taxiing at Royal Air Force stations across Lincolnshire and Yorkshire. Another four-engine bomber, the analysts at Luftwaffe intelligence headquarters in Berlin, barely looked up from their desks. Britain had been churning out heavy bomber designs since 1939, and most of them were frankly rubbish. The Sterling couldn't climb above 15,000 feet without wheezing like an asthmatic pensioner. The Halifax kept shedding tail units mid-flight. And the Manchester? That twin-engine catastrophe was already being withdrawn from service after spending more time in maintenance hangars than over Germany. So when photos of this new aircraft, designated Type 464 in early intelligence reports, landed on German desks, the assessment was brutally dismissive. 4 Rolls-Royce engines, conventional mid-wing design, twin tail fins, nothing revolutionary. Just another British attempt to cobble together a credible strategic bomber from an industry that seemed incapable of matching German or American engineering standards. The wingspan measured 102 feet, putting it squarely in the same category as every other lumbering 4-engine design cluttering RAF airfields. Oberst Josef Schmidt, Chief of Luftwaffe Intelligence, filed the Type 464 reports alongside dozens of other British aircraft that posed minimal strategic threat. The German assessment wasn't entirely unreasonable. Britain's heavy bomber program had been an absolute shambles. For 3 years, the Air Ministry kept issuing contradictory specifications, demanding aircraft that could somehow be both long-range, strategic bombers and tactical support platforms. Manufacturers responded with compromised designs that excelled at nothing. The short Sterling, Britain's first 4-engine heavy bomber, entered service in August 1940, but was already obsolete. Its massive landing gear and short wingspan meant it could barely reach operational altitudes, where German fighters and flak did their worst work. Crews called it a death trap. German intelligence had thoroughly documented these failures. Interrogations of downed RAF aircrew revealed chronic mechanical problems, inadequate defensive armament, and abysmal bomb loads that barely justified the fuel consumed. Getting to target and back. When Luftwaffe analysts compared British heavy bombers to their own Heinkel, He-177, or even to American designs like the B-17 Flying Fortress, the conclusion was obvious. Britain had lost the heavy bomber race before it even started. The Type 464, soon to be designated the Lancaster, arrived at No. 44 Squadron at RAF Waddington in December 1941 for operational trials. German observers noted the squadron code KM appearing on reconnaissance photos throughout January and February 1942, but saw nothing worth elevating to high command. It looked like every other British 4-engine bomber. 4 engines, 7-man crew, dorsal and tail turrets for defence. The only notable difference was those twin tail fins instead of the Halifax's single large rudder. But that was merely a design variation, not a capability revolution. What German intelligence completely failed to grasp, what their rigid assessment criteria couldn't detect from grainy reconnaissance photographs, was the revolutionary space between those wings. While analysts catalogued engine types and measured wingspans, they missed the one specification that would redefine strategic bombing. The Lancaster's bomb bay ran unobstructed for 33 feet through the aircraft's centre section. No structural beams, no fuel tanks, no intrusive supporting framework. Just open volume waiting to be filled with tonnage German engineers thought physically impossible to carry. The story behind this unobstructed bomb bay begins with one of the most spectacular failures in British aviation history. In July 1936, The Air Ministry issued specification P-1336 calling for a twin-engine medium bomber capable of carrying 8,000 pounds of bombs over 2,000 miles. The logic seemed sound. 2 engines meant lower production costs, less fuel consumption, and easier maintenance than 4-engine designs. Avro Aircraft's chief designer Roy Chadwick responded with the Type 679, later christened the Manchester. It looked brilliant on paper. The Manchester first flew on 25th of July 1939, and problems emerged immediately. Chadwick had been forced to use the Rolls-Royce Vulture engine, a 24-cylinder X-configuration beast that produced 1,760 horsepower. On paper, 2 Vultures could match the power of 4 smaller engines. In reality, the Vulture was an absolute disaster. The engine was essentially 2 Rolls-Royce Peregrine V12 engines mounted on a common crankcase, and that crankcase couldn't handle the stress. Connecting rods failed, cylinders cracked, coolant systems leaked. The Vulture overheated in level flight and caught fire with disturbing regularity. Number 2, 107 Squadron received the first operational Manchesters in November 1940, and within months, the aircraft had established a reputation that terrified its own crews more than German defences. On the night of 24th of February 1941, Flight Lieutenant Sherwood's Manchester suffered engine failure 20 minutes after takeoff. He coaxed the dying bomber back across the North Sea on one engine, but 3 crew members bailed out over England, certain they were about to die. On 13th of April, another Manchester lost both engines over Germany. The entire crew was killed. By June 1941, Manchesters were being withdrawn from operations after barely 6 months of service. But here's where desperation sparked genius. Roy Chadwick refused to accept that his fundamental airframe design was flawed. The Manchester's fuselage was sound. The wing structure was solid. The enormous bomb bay, designed to accommodate 8,000 pounds, was exactly what Bomber Command needed. The only problem was those cursed Vulture engines. So Chadwick did something brilliantly simple. He threw the Vultures in the bin and started again. The solution required extending the wingspan from 80 feet to 102 feet and mounting 4 Rolls-Royce Merlin engines instead of 2 Vultures. The Merlin was already powering Spitfires and Hurricanes with legendary reliability. Each Merlin 10 produced 1,280 horsepower, less than a Vulture individually, but 4 Merlins together delivered over 5,000 horsepower with none of the catastrophic failure modes. Chadwick's team worked with ferocious speed through late 1940 and early 1941, redesigning wing spars, recalculating weight distribution, and reworking fuel systems. The first Lancaster prototype, converted from a Manchester airframe, flew on 9th of January 1941 from Woodford Aerodrome. Test pilot Sam Brown reported the aircraft handled beautifully, with none of the Manchester's vicious tendencies. The engines purred. Controls responded smoothly. Most critically, that cavernous bomb bay remained completely intact. Chadwick had taken Britain's worst operational bomber and transformed it into something unprecedented. The Air Ministry, desperate for anything that actually worked, ordered immediate production. By Christmas 1941, the first Lancasters were arriving at operational squadrons. German intelligence documented this transition but interpreted it as Britain simply replacing one mediocre bomber with a slightly less mediocre variant, 4 engines instead of 2. That just meant more fuel consumption and maintenance headaches. They couldn't have been more catastrophically wrong. The Merlin engine sitting in each Lancaster nacelle was the same basic power plant that had saved Britain during the Battle of Britain, but what it accomplished in a heavy bomber was something else entirely. Each Merlin 20 or 22 produced 1,000 460 horsepower at takeoff, and these engines could maintain that output hour after hour without the dramatic failures that plagued German and even some American designs. Rolls-Royce had spent years perfecting the Merlin's liquid-cooled V12 configuration, and by 1942 it was arguably the most reliable aircraft engine in the world. Lancasters routinely flew 7-hour missions to Berlin and back, with all 4 Merlins running smoothly, whilst German bombers were still struggling with engine reliability over much shorter distances. But raw power was only part of the equation. What made the Lancaster truly revolutionary was how Chadwick's team had engineered the entire airframe around that unobstructed bomb bay. In every other heavy bomber of the era, German, American or British, the bomb bay was interrupted by structural supports, fuel tanks or equipment bays. The American B-17's bomb bay was divided into 4 separate sections by major structural beams. The Halifax had fuel tanks running through its bomb compartment. Even the Sterling, despite its size, could only accommodate bombs up to 2,000 pounds because of internal structural limitations. The Lancaster's bomb bay was different. Chadwick had designed the main wing spar to pass over the top of the bomb compartment rather than through it. This seemingly simple decision, moving a structural element a few feet higher, created 33 feet of completely unobstructed vertical and horizontal space. The bay was 9 feet wide and ran from just behind the cockpit, nearly to the tail section. You could stand in it, you could walk through it. More importantly, you could hang absolutely enormous bombs in it. When the Lancaster first entered service in early 1942, it could carry 14,000 pounds of standard bombs to targets in Germany, more than 3 times what German intelligence believed possible for an aircraft of its size. The typical load consisted of one 8,000-pound high-capacity bomb plus smaller weapons, or various combinations of 4,000-pound cookies and incendiaries. German analysts who interrogated captured Lancaster crews in mid-1942 initially dismissed their claims about bomb loads as either exaggeration or confusion about total squadron tonnage versus individual aircraft capacity. The physics seemed impossible to German engineers. An aircraft weighing 68,000 pounds, fully loaded, shouldn't be able to carry 14,000 pounds of that weight as bombs. That was more than 20% of maximum takeoff weight devoted to payload. German heavy bombers typically managed 8 to 10%. The Heinkel He-177, Germany's only operational 4-engine bomber, could carry 4,400 pounds maximum. Even that required reducing fuel load for shorter range missions. What German calculations missed was the Lancaster's extraordinary power-to-weight ratio and aerodynamic efficiency. 4 Merlins producing nearly 6,000 horsepower combined gave the Lancaster enough thrust to haul massive loads whilst maintaining operational altitude. The aircraft could cruise at 20,000 feet fully loaded, high enough to avoid the worst flak concentrations. Maximum speed at that altitude was 287 miles per hour, fast enough to make interception difficult for all but the most skilled night fighter pilots. The wing design contributed significantly to this performance. That 102-foot wingspan generated enormous lift, whilst the relatively clean aerodynamic profile minimized drag. Chadwick had obsessed over every detail that might reduce air resistance: flush riveting where possible, carefully faired engine nacelles, streamlined turrets. The result was an aircraft that could carry unconscionable amounts of ordnance over operationally useful distances whilst still handling like a fighter by heavy bomber standards. By late 1943, the Lancaster had already proven it could haul 14,000 pounds routinely. But Barnes-Wallis at Vickers Armstrongs was thinking bigger, much bigger. Wallis, The engineer who designed the bouncing bombs for the dam's raid had become obsessed with earthquake bombs, weapons so massive they didn't need to hit targets directly. Instead, they'd penetrate deep underground and create shockwaves that would shatter foundations and collapse structures from below. His calculations showed these weapons needed to weigh at least 10 tons to achieve the required penetration depth and destructive effect. 10 tons, 22,000 pounds. The Air Ministry thought Wallace had lost his mind. No bomber in existence could carry such a weapon. The Lancaster's maximum bomb load was 14,000 pounds, and that was already stretching the aircraft to its limits. Asking it to carry an additional 8,000 pounds seemed not just ambitious, but physically impossible. The wings would snap. The undercarriage would collapse on takeoff. The engines couldn't generate enough power to maintain altitude. Every structural engineer who reviewed Wallace's proposal said the same thing. Fascinating concept, completely impractical delivery method. Wallace disagreed. He'd studied the Lancaster's design specifications obsessively and believed the airframe could handle far more stress than its official ratings suggested. The key was that cavernous bomb bay. A standard Lancaster could carry 14,000 pounds of multiple bombs distributed across the bay's length. But what if you hung a single weapon from the strongest structural points? What if you stripped out unnecessary equipment, some of the armor plating, defensive guns from positions German night fighters rarely attacked from, even the bomb bay doors? What if you used the most powerful Merlin variants and accepted reduced fuel load for shorter range missions? Avro's engineers ran the calculations and reached a stunning conclusion. Yes, a modified Lancaster could theoretically carry 22,000 pounds. Not comfortably, not safely by peacetime standards, but it could be done. In May 1943, the Air Ministry authorised development of the Tallboy, Wallace's 12,000-pound earthquake bomb. This would serve as a stepping stone to prove the concept before attempting the even more ambitious Grand Slam. The first Tallboy was dropped on 8th of June 1944 by squadron leader Jock Calder, flying a modified Lancaster from No. 617 Squadron. The target was the Saumur railway tunnel in France, critical to German reinforcement efforts after D-Day. The Tallboy punched through 70 feet of soil and rock before detonating, collapsing the tunnel so completely that it remained blocked for years after the war. German engineers examining the damage couldn't comprehend what weapon had caused such destruction. Their initial assessment suggested multiple bombs hitting simultaneously, because surely no single weapon could generate that much force. More Tallboy strikes followed through late 1944. On 15th of September, Lancasters carrying Tallboys attacked the Tirpitz in Kafjord, Norway. One bomb struck the battleship directly, punching clean through her armoured deck and blasting a hole in her bottom. The Tirpitz never sailed again. German naval intelligence requested urgent information about this new British superweapon, but Luftwaffe analysts had no answers. Their fundamental assumptions about Lancaster capabilities had been wrong from the start. Then came the Grand Slam. First dropped on 14th of March 1945 by squadron leader Charles Calder, yes, related to Jock, against the Bielefeld Viaduct in Germany. The 22,000-pound bomb was 35 feet long, with a hardened steel case designed to penetrate 100 feet underground before detonating. The Lancaster carrying it had been stripped of nearly everything non-essential. Mid-upper turret removed, bomb bay doors removed, nose turret replaced with a streamlined fairing. Even some cockpit